Hello listeners, I am Dr. Anuj Sharma, working in Center for Advanced Studies in Mechatronics program as a coordinator there. It is the in-campus research driven institute of Dr. APJ Abdul Kalam Technical University located in Lucknow. So, we are discussing the topic, the subject fundamentals of mechanical engineering and mechatronics. So, today in this particular lecture, we will discuss the some problems, numerical problems on shear force and bending moment diagrams, how the different bending diagrams can be drawn. If time will permit, we will take as much as number of problems to understand the concept of BMD and SFD. So, these are the outlines. I will discuss the brief of SFD and BMD. Already we have discussed in the previous lecture, but we will take very brief and the numerical problem on SFD and BMD. So, what is the shear force? Shear force, let us recapitulate. It is the total, let us say this is W 1, W 2 and this is reaction R 1, R 2. So, the shear force is what? Shear force is the algebraic sum of all the vertical forces acting on any particular section. Let us say this is the section 1 1. So, on the left side we will see the algebraic sum of all the forces. So, just add these forces. Let us say shear force 1 1 is equal to, so R 1 is positive upward minus W 1 minus W 2. So, likewise we can calculate the shear force at any point. Let us say if you want to calculate the shear force at this particular section. So, let us say this section is 2 2. So, what would be the shear force? So, shear force 2 2 will be equal to, so that is the R 1 minus W 1. So, likewise we can calculate the shear force at any particular point, and for the sign convention we will always see the left side, and if the forces net forces are acting or any forces are acting on the upward direction. So, we will consider that force as positive, and if it is if it is acting downward, then we will consider it as negative, and we will always see the left side of the point or section, whatever you will assume. So, we will always consider the left side. Understood? Similarly, for the bending moment, we will consider the bending moment is also like this. So, if this is the beam and two forces are acting on the left side of any point, and if we know the distance of these points from this point, these forces. So, let us say this is the R 1, this is W 1. So, if we write it as sigma m about, let us say this point is C. So, C, if you want to, we will always see the left side and calculate the movement of all the forces which are acting on the left side, calculate their movement and add them algebraically. You will get the overall movement, bending movement at this particular point. So, let us say for this case it would be R 1 into total distance is how much, that is L 1 plus L 2 from this point. So, this distance is L 1 plus L 2 and this bending moment will be clockwise. So, that is why it is positive. Now, the next moment is anti-clockwise. So, it is W 1 into L 2, or for simplicity you can remember that if on the left side the force is positive, its bending moment will always be positive, because we are actually looking at the left side only. So, if we are looking at the left side, so we can make it more simpler by assuming that if the force is positive, its bending moment will be positive. If force is negative, means it is acting downward. So, it will create the counterclockwise movement. So, then that movement would be negative. So, it is more simpler to remember. Now, we will take some problem. So, let us start with a very simple problem. So, let us say this is the beam. So, this beam is AB whose length is given, this is L. Now, let us say it is simply supported. So, it is supported by two supports. Let us say this support is R 2, this support is R 1. Now, this is the very simple situation where we are assuming that this is the load W which is acting at the midpoint. So, it means this distance is L by 2, this distance is L by 2. And I have already told you, or if you have not attended my previous lecture. So, I am just about to tell that always keep the space below the beam empty till you solve the problem, because we will draw the SFD and BMD diagrams on just on the area just below the beam. So, that we can have the projections of different points on the corresponding diagrams. So, that would be easier for interpretation, right. So, now first calculate the reactions. So, reactions you can calculate. So, here I know it is very simple case. So, when you will solve the reactions, it will be W by 2, W by 2, because it is the case of symmetric. But we have already, you can refer my previous lecture to calculate the reactions, how to solve the reactions of beams. So, now what we can do? Now, we can divide this beam into different area, because this in different segments. So, from A to B, because there are the variation in the load. So, we cannot consider this as a continuous length. So, you can see from A to this point, midpoint. So, let us say midpoint is C. So, from A to C no force is acting, and at point C this load is acting. So, it means some quality or characteristic would change here. So, what you can do? You can divide this in two segments. One segment is A to C, another segment is C to B. So, likewise, so we will consider two regions. So, what you can do? So, consider, let us consider one section, let this section is 1 1. So, first we calculate the shear force. Please see carefully. So, shear force at, first we want to calculate shear force. So, shear force at 1 1, this cross section. So, what would be the shear force? You put your hand or finger or whatever you have in your hand, you can put here and just see on the left side. So, how many forces you are able to see on the left side? So, we are able to see only one force on the left side, and that is vertically upward. So, it means it is equal to the R1, or we can say it is equal to W by 2. So, it means on this particular section how much is the shear force? That is the W by 2, right. So, this is the basically equation, and W by 2 is a constant. So, this is the kind of straight line equation, y is equal to C, right. So, this is a equation, shear force is equal to some constant. So, now how we can see the shear force value at point A or at point C or in between point A and C. So, for that I have simple logic. So, just you can write just left to point A or just before point A. If we put here, so what force you are able to see? If I consider my hand here, so are you able to see any force on the left side? No. So, shear force would be equal to 0. So, it means the shear force just before the reaction or just before the point A is what? 0. And when you come to the just right side, so just I am writing it as just after. So, this is the just after point A. Shear force would be how much? So, when you come just after means just crossed the point A. So, the shear force would be how much? One force, that is how much? W by 2. So, shear force is W by 2. Now, come to the point C, because in between no variation is there, no force is there. So, whatever shear force would be here, whatever shear force would be here, 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 you will have the same value, because no another force is being added. So, when you will come close to point C, so we write it as like this, because this is the equation, this equation will be valid for x less than L by 2 and less than greater than 0. So, when, because you have considered this section, this 1 1 section at a distance of x from here. So, when x, the value of x would be 0, this formula will be applicable. When you will come to the point C, so all just before point C means the distance is just less than the L by 2, you will get the shear force W by 2. But when you will cross the point C, you will be entering into the different segment. So, this equation would not be valid for that reason. So, this equation is valid till this region only. Okay. So, now just after, so for just after C, so first we can see we completed just before C, shear force is how much? Again W by 2. Now, for just after you will have to write another equation. So, shear force at section 2 2. So, let us consider shear force. So, we what we do? We consider another section 2 2 at a distance of x from here. So, now what would be the shear force now? So, that shear force would be equal to, now you see the left side. So, left side is W by 2, this reaction upward, and minus W, this force is downward. So, what is the value? Minus W by 2. Am I correct? Okay. So, now just अब you can apply this equation. Now, this equation would be valid. So, it is for x greater than L by 2 less than L. So, for this reason this equation would be valid. So, just after C, shear force would be equal to how much? Minus W by 2. Just before C, minus W by 2, right, and just after when you cross the point P. Now, what is the total force on the left side? Total beam is on the left side. So, if total beam is on the left side, means when you will add W by 2 minus W plus W by 2, again it will be 0. So, you can see interestingly from here the bending moment just before the first point and just after the last point will always be 0, right. So, now we have to draw this shear force. So, this is the x axis. So, along the x axis what we draw? We draw the length of the beam. So, we don't need to be worried because we have projected all the points below this beam. So, whatever the length that would automatically be projected in the lower area and we can get this particular x axis. Now, on the y axis we have to draw these points. Now, carefully see, this is the point A, this is point B and this is the point C. If we project this, this is the C. Now, you see just before, just left to A, matlab before A, what is the shear force? That is 0. Okay. Just after A, what is the shear force? W by 2. So, just after and just before, basically if you will see carefully, so all these points will coincide each other. So, this is the force W by 2. Now, just before C and just after C, just before C it is W by 2 and just after C it is minus W by 2. It means there is a variation from left to right. So, it means at point C we have two values. So, just before C means this is the W by 2 and just after C we will have different value minus W by 2, right. So, from here to here how we should add. So, this is the equation of a straight line. So, you can match these 2 points by straight line, then you can come because these points are expected to be lie on the same point. So, this is the point and just before B what value we have? Minus W by 2. So, this is minus W by 2. So, we can match this point and just after B what is 0? 0. So, we can match. So, this is positive, this is negative and this is the shear force diagram. So, this is the shear force diagram. So, you can see from here. So, if we will vary from, we will move from here to there. So, initially the shear force was 0, but at this point it was W by 2, it remained constant till the middle point, then it dipped down to minus W by 2, then it remained constant till the end of the beam. So, this is the shear force diagram. So, where the shear force is 0? At C 0, at A 0 and B 0. So, at these 3 points the shear force is assumed to be 0. Now, the bending moment diagram. So, bending moment diagram. So, what we can see? So, just on the same principle what we can do? We can calculate the bending moment at different points. So, because bending moment depends upon the distance. So, just before and just after it will not have any impact on that. So, we will do here itself and we will see how this bending moment can be calculated. So, I do not want to skip this slide because I want to refer this beam again and again. So, let us say for bending moment diagram. So, at A, so bending moment at A point, bending moment. So, any force, are you able to see any force on the left side? No. So, it means bending moment is 0. So, at point C, bending moment is what? At point C, if you will see, we have only one force on the left side. So, what would be the bending moment of this point? So, the bending moment of this point would be W by 2 multiplied by this L by 2. So, this distance is what? This distance is L by 2 and this moment will go like this clockwise. So, what would be the bending moment? It would be W L by right. So, W into W by 2 and the distance is L by 2. So, it would be equal to W L by 4, right. Now, if you want to calculate the bending moment at point C, so if you see at this point these two forces are on the left side. So, if we calculate the bending moment at this point, so that would be equal to W by 2 into L. So, that is the clockwise about this point also, but the total distance would be how much? Total distance would be L. So, it is W by 2 into L clockwise minus this force, it is acting downward. So, that would be W into L by 2. So, minus W into L by 2. So, what would be the bending moment at point C? So, W L by 2 minus W L by 2, it is again 0. So, interestingly you can see here on the left and right extreme points the bending moment will always be 0. So, now if we will draw this bending moment diagram here. So, first draw the beam. So, this is the point A, this is the point B and this is the point C. So, at point A the bending moment is 0. So, mark this point because on y axis we are taking the bending moment value. So, on this y axis the bending moment is 0. So, this is 0, on B again the bending moment is 0 and on C the midpoint the bending moment is W L by 4. So, let us say W L by 4. Now, how we can add this point to this point? So, you can see here it is bending moment is means y is equal to constant, W is constant, length is constant. So, W Bm is equal to constant. So, we can compare this with this equation. So, y is equal to C. So, it means it is a straight line. So, we can add these with this cell. Now, but from here it is not coming, actually you can calculate the bending moment like this. Let us say bending moment you want to calculate at section 1 1. If you want to calculate this bending moment at this, so what would be the equation of this? So, if you will see, because it was very simple, so I use this, otherwise we can calculate the bending moment at this particular section. So, if you want to calculate bending moment at 1 1, what it would be? It would be W by 2 multiplied by x. So, I should write like this. So, that is why it has come inclined line. So, y is equal to mx. So, this is y means bending moment in y direction, this is the slope of the line W by 2 and this is the x. So, this that is why this line has come like this. Similarly, if we will write equation for this, that will also have bending moment 2 2, that will come like this, W by 2 into what would be L by 2 plus x, this is the clockwise about this point we are looking, and minus W this into x. So, again it is the straight line, the inclined line. So, you can make like this. So, this is the positive value and this is the bending moment diagram. So, you can easily see from here. So, where the shear force is 0 at this point, you are getting the bending moment maximum here. So, what is the maximum value of the bending moment for the simply supported beam? It is W L by 4, right, understood. So, I took a lot of time to solve this problem just to convey you the understanding of this particular topic. Now, we will consider another problem. Let us say this is the problem number 2. So, if we draw the beam, we take the beam little bit more complicated as far as the loading is concerned. So, let us say this is the point load, this is the uniformly distributed load. So, how it can be solved? So, let us say this is the reaction R1, this is reaction R2 and this is the W intensity, W Newton per meter and total length of the beam is L. Now, here interestingly we can see it we not need to divide into different segments, because only this is the load, uniformly distributed load, which is varying from one end to the another end. So, no need to write any the division of this beam into different segments. So, we can take only one segment. So, from the uniformity, or we can say the symmetry, we can have the value of R1 as W L by 2 and R2 again WL by 2. So, W into L is the total load, will be shared equally by these two supports. So, you can easily calculate the reactions also. So, now what we can do, we can project, we can keep this area vacant for our bending moment and shear force diagram. So, now you can take one section. So, let us say this is the section 1 1 at a distance of x from here. So, what would be the shear force at this point? So, shear force, so you can write heading section 1 1. So, shear force 1 1 is equal to, that would be how much? So, that would be, if we will write it as R 1 into x, sorry, this would be R 1. So, this is only R 1, R 1 upward. What is the total force? We are calculating the shear force only. So, R 1 upward means positive, and the total value of this, what is the total value of this? The intensity is W, length is x. So, that would be minus W into x. So, this is the equation of the shear force, and that would be valid from x 0 to L, complete for whole length it would be applicable. So, at just before point A, shear force will always be 0, no need to take tension. Just after A, x would be equal to 0. At this point A, x would be how much? 0. So, shear force is, when you will put x is equal to 0 in this expression, you will get R 1. R 1 is how much? This is W L by 2. Now, just before B, x would be how much? When we will reach here. So, just before this point, what would be the value of x? That would be the complete length. So, it is L. So, shear force is equal to, so you will put this x is equal to L in this expression. So, what you will get? R 1 minus W into L. So, that would be equal to W L by 2 minus W L. So, that would be minus W L by 2. So, shear force at this particular point, just before this point, that would be minus W L by 2, and after B, if you will x is equal to L plus something. So, again that would be, and plus this. So, it means you have come here. So, if you will see, this is W L by 2 minus W L plus W L by 2, that again shear force will be equal to 0. So, you draw the shear force here, this is the beam length, and what you will see at this point, the shear force is 0 on the left side, and on the right side just after A, the bending moment is shear force is W L by 2. So, you can match these 2 points. Now, just before B, the value is minus W L by 2, means when we reach here, so we get the value here. So, it is minus W L by 2. So, you can match this, and on the right side it is 0. So, we can match these 2 points. Now, how we will match these 2 points? So, you can see this is the equation of straight line. So, R 1 means W L by 2 minus W x. So, that would be the straight line. So, you just connect these 2 points by straight line. So, this is the positive, this is negative. So, you can see the variation of shear force from here to there. So, let us say this is the point A, this is point B. So, at this point, at the middle, the shear force would be 0. So, it means the bending moment must be maximum at this point. So, now take the bending moment. If we draw the bending moment diagram. So, at now bending moment. So, at point A, or you can write the bending moment equation here itself at this point, section 1 1. So, at section 1 1, so bending moment would be how much? So, that bending moment would be how much? You write the bending moment equation here. So, that would be equal to R 1 into x. At this point you are writing the bending moment equation. So, it would be clockwise minus this whole force, this will act here. So, the bending moment of this section about this point section 1 1 would be equal to the load would be equal to W into x, and that will act at a distance of x by 2. So, what would be the bending moment? That would be in the anti-clockwise direction, that would be W into x by 2. So, you can see here the equation is quadratic. So, R 1 means W L by 2 into x minus W x square by 2. So, it is the quadratic equation and it would be valid from left to right for whole length. So, now at point 8, at point A, x is equal to 0, bending moment would be equal to 0. This point, put the x is equal to 0 in this equation, you will get the bending moment 0. At point B, bending moment will be equal to, means x would be equal to how much? X would be equal to L. So, when you will put x is equal to L here, so it would be W L square by 2 minus W L square by 2, again it will be 0. So, it means we are not getting any information. If we will draw the bending moment diagram here, so at this point the bending moment is 0 and at this point the bending moment is 0. Now, how should we connect these 2 points? So, that is a problem. So, either we can connect, so which curve should we use to connect it? So, that is clear from here, it should be parabola or quadratic. Parabolic or quadratic, whatever it is. So, either it can go like this or it can go like this. So, except these two options we do not have any third option. So, either it would be upward or downward, that we will have to see. So, what you can do? You can calculate the bending moment. So, we need 3 points to draw the parabola or quadratic functions. So, what you can do? You can calculate the bending moment at this point, middle point. So, calculate the middle point for this. So, put x is equal to L by 2 in this expression. So, put x is equal to L by 2 in equation. So, we will get bending moment equation is equal to W L by 2. So, W L by 2 into what is the x by 2 means it is the W into x is L by 2, right, and x again L by 2 into 2, so L by 4 minus. So, that would be W into x square by 2, x is L by 2. So, L square by 4 into 8. So, it would be equal to W L square by 8, and here it is W x, sorry, it is R 1 x. So, that would be equal to it, we will not have this. So, this is W L by 2 into L by 2, sorry. So, what it will get? So, we will get here W L square by 8. So, it is the positive value, whatever the value is, but it is positive value. So, it means the third point would be here. So, we can match these 3 points like this, and this height is how much? This height is W L square by 8. So, this is a positive. So, like you can see the shear force is 0 here. So, we got the maximum bending moment at this particular point. So, many things are important here to note, that if we have in the previous case, you see the previous slide, if the shear force line is horizontal, the bending moment line will be inclined, right. If the shear force line is inclined, bending moment is parabolic. It means the bending moment is just 1 degree ahead of the previous shear force diagram. So, if the shear force diagram is parabolic or quadratic, then the bending moment would be cubic function. So, we can just see here. So, if this kind of loading you will get. So, in this case shear force diagram you will get quadratic function. So, I am just writing for you, and for bending moment diagram you will get cubic function. So, 1 degree ahead. So, please take care of this, and you do practice at your home. I hope you have understood the concept of bending moment and shear force diagrams. Now, you practice at your home to draw the SFD and BMD of different types of beams under different loading conditions. So, thank you for watching this video. Thank you so much.